Who would like to take a ride on Snoopy's doghouse, the most advanced aircraft ever made? Join us today, and we're going to take a ride on Snoopy's doghouse. We're going to travel around the world discussing about the Airbus A350. Welcome to our presentation of findings for Carleton University CCDP 2100 class, Section B. Today is June 15th, 2022. Accompanying myself is Finn, Stefan, and Jaden. So why should this matter to you? Well, for starters, air travel has come a long way. At first, it would take us 2 months to go from Europe to Canada. Well, now we can make that same trip under 6 hours. The beauty of this aircraft is that it has reduced air flight pollution by over 25% in the last few years. Our itinerary today includes, we're first going to start off in Canada and make way to Netherlands, where Jaden will discuss wing design. Afterwards, we're going to circle down and go down to Egypt, where I will discuss the airframe. Afterwards, Finn will take it away and we'll discuss in Germany about the engine. And lastly, Stefan will take us to Dubai, where he'll discuss the avionics. And now, without further ado, I'm going to hand off to Snoopy, who's going to get our first leg of the trip underway. Now we're going to begin our first leg of the trip going from Ottawa to Netherlands, where we're going to meet Jane, who's going to discuss wing design and how wing design is able to keep the aircraft in the air.
Thank you, Victor. Have you ever wondered how a plane is able to generate lift? Here we are in the Netherlands, where a Dutch scientist named Daniel Bernoulli was born. Now, he probably didn't know this at the time, but in his life, he would discover a theory that would enable us to fly. Today, I will be discussing the wing design of the Airbus A350. Specifically, I'll be using Bernoulli's principle to explain how changing the shape of a wing over the course of a flight can increase the fuel efficiency. First, I'd like to explain how a plane is able to stay in the air. Now, I can explain that using the airfoil here. An airfoil is like a cutout or a cross section of a wing. So if I was to slice a wing and then take one slice out, that would be the airfoil. Generally, they are made of a curved top and a flat bottom, as you can see in figure 15. The wings are shaped this way because of something known as Bernoulli's principle. Bernoulli studied fluids like water and air, and he found that faster moving fluids have a lower pressure, while slower moving fluids have a higher pressure. In the context of a wing, when a plane starts flying and the air hits the wing, you are going to get faster moving air on top, and it is going to speed up because of the curve. You will have slower moving air on the bottom to match. The fast air creates low air pressure on top, while slower air creates high air pressure on the bottom, as you can see on the left in figure 14. That high air pressure pushes upward on the plane, and that's what makes something as large as a plane fly. Now, it is important to remember that all pressure differences are not created equally. As a plane changes its angle between the wind and the wing, more or less fuel must be consumed. Figure 16 shows this using colors. In this case, blue would represent the least amount of fuel needed, followed by green, then yellow, orange, and finally red would require the most amount of fuel to stay in the sky. What is important here is that as the angle changes, so does the amount of fuel needed. The same is true for a larger aircraft that wants to fly in a relatively straight line, and it has air that is flying in all sorts of directions at it. Traditionally, in order to deal with adverse air conditions, the plane would have to speed up and use more fuel to overcome this. The Airbus A350, however, provides a far more eco-friendly solution because it uses something known as a variable camber wing. A variable camber wing can change its shape in order to match the wind instead of the other way around. As a result, in cases like figure 17, where the wind would normally make higher fuel consumption necessary, the plane can simply change the wing so that it can keep flying in a straight line without using any additional fuel. As a result of needing less fuel to do the same job, the Airbus A350 has used wings to become a highly environmentally friendly plane. Now let's fly down to Egypt, where Victor is going to explain the airframe which holds the plane together.
Thank you, Jane. Welcome to the second leg of our adventure. Welcome to Egypt. My theory is the theory of composites. Ancient Egyptians first discovered this principle back in 1500 BC. What they would do is they would take their mud bricks as well as their boats, and they would reinforce both of them using straws that increase the durability and the strength of both the mud bricks as well as the boats. Today, we'll be discussing the airframe. But what is the airframe? The airframe is the entire solid structure of an aircraft, excluding the engines. So as we can see here in figure 23, it is everything here, everything in blue, minus the engines. Now, my research question here is, how does using new composite materials reduce fuel consumption and the overall cost while still meeting safety standards? Now, to help us answer this question, we're going to be using the theory of composites. Now, on this particular aircraft, over 53% of the aircraft is made using composite materials. So referring to figure 23 once again, everything here in blue is made of composite materials. But what is a composite material? Composite materials consist of two parts. We first have the fiber / the filament that acts as a reinforcement, as well as a matrix that acts as the host body. When we combine the two together, we produce a composite material. Now, the beauty of composite materials is we're able to drastically increase the strength of individual materials when we combine them together, but while keeping their weight at a bare minimum. Just to get a rough idea on the strength of composite materials, if we were to try and break composite material under pressure, we would need to go 40 times deeper than the bottom of the ocean to reach the pressure necessary to break a material in half. Referring back to the airframe, majority of the airframe on the Airbus A350 is made using composite materials. Now, these composite materials have a special type called laminates. And what laminates are is they consist of layer after layer of composites added on top of them. So we can see here back on figure 24. This is similar to painting a wall. You first start off with your base or your primer coat, and we add layer after layer after layer until we reach our desired finished coat. So you can see here figure number 26. But let's dive in even deeper into composite materials, specifically the fiber / filaments I mentioned earlier. They consist of very long strands of carbon atoms, similar to the ones we see here on figure 27. And then we keep adding and adding and adding more and more carbon atoms. We produce these very long strands of carbon fiber, similar to figure 28 here. And we add more and more fibers, or we produce the weaving patterns, we produce composite materials. And as soon as we add the matrix into it, we now have a complete composite body. Referring back to the airframe and the Airbus A350, as we can see here in figure 29, we have an automated process used for layering composite materials. We first start off with our mold, and then we use this industrial machine that goes row by row, layer by layer, adding composite material. Once all that's been finished, we bring the mold and the wet composite into an oxygen-free curing oven that's used to harden and solidify composite material. Once all that has been done, we will take the composite material and undergo safety testing. The most noticeable test performed is the lightning strike test, as we can see here in figure 31. As we see here, this burnt patch is actually not the composite material burning. It's actually a metallic mesh that they mix with the composite material that's used to protect the composite as well as the airframe from any lightning strikes mid-flight. Other tests we perform are bird strike tests, hail, corrosion tests, and all those tests yielded the composite materials are much sturdier and much stronger than regular traditional materials. Now, the one downside is composite materials do cost more upfront because we first have to mold them, then layer them, then solidify them, which all cost time and money. But overall, they are much stronger and much more durable than regular materials we use today. To summarize everything we just discussed, my research question was, how does using new composite materials reduce fuel consumption and the overall cost while still meeting safety standards? As we mentioned earlier, composite materials are incredibly strong, but also incredibly light. However, they may cost more upfront to produce, but they also require less annual maintenance in the long run. After performing a bunch of safety testing, we concluded that they performed remarkably well and some much better than traditional materials we have today. Now that's all for me. I'm going to pass it off to Finn to take us to Germany and discuss how the jet engine and how it gets the aircraft in the air in the first place. Thank you.
Thank you, Victor. Today, we are in the home of the first law of thermodynamics, Germany, explained by Rudolf Clausius, a German physicist and mathematician. The first law of thermodynamics is all about energy conversion. In simple terms, the amount of energy in the universe is constant and it just keeps changing form. My subtopic is the jet engine of the A350, and we will discuss the first law of thermodynamics and how an increased bypass ratio improves fuel efficiency. As said earlier, the first law of thermodynamics is all about energy conversion. In a jet engine, the fan increases the amount of kinetic energy going into the engine. Then the kinetic energy will continuously be increased by pressure and temperature with the use of the compressors and combustors seen in figure 35. The kinetic energy is used to propel the plane forward, and a secondary use is to produce electricity for the aircraft via turbines. An increased bypass ratio increases the amount of air going into the compressor, which reduces the amount of fuel needed to produce the same amount of kinetic energy. So in conclusion, increasing the bypass ratio increases the airflow into the core. And when the airflow into the core is increased, the fuel requirement is reduced, therefore improving the fuel efficiency. So that concludes my part. We will now go on with the third leg of our journey to the UAE, where we will discuss the avionics with Stefan.
We have composite materials and we have a repeatable engine. But now, how do we control all this? Hello everyone, my name is Stefan and I will be speaking about the avionics aspect of this project. Avionics is simply the combined force of aviation and electronics that allows pilots control the plane's activities. My research question wishes to know how automated control systems can reduce fuel consumption. And to answer this, I will be talking a little bit about control theory. What's control theory? It's a series of mathematical computations that allow a system to respond adequately based on external stimuli. Essentially, in our case, when certain external factors act upon the plane, we want to have a system in place that understands just how to respond to the situation appropriately. Figure 42 depicts a simple schematic of the process in which control theory works. A sensor first collects data, which acts as input. Then, in comparison to a reference value, the error in the input is measured and accounted for by the compensator, which then recalibrates the input to produce the desired output by the system. Figure 43 tells us a simple story of how car manufacturers often employ people to work on their cars. However, oftentimes due to human error, they have to keep redesigning and remodifying. Such incurs significant costs. But with automated robotic arms as seen in figure 44, manufacturers can benefit from the precision, speed, and efficiency of such technology. Now, circling back to my research question, I believe automated control systems in airplanes can reduce fuel consumption by 1. Having minor aspects of flight protocols guaranteed to be completed to the set standard. 2. Engine use can now become a function of flight requirements, meaning no longer will pilots have to employ their discretion to ascertain how long they need to warm the engine up for, or how many engines need to be online at any point during the flight. 3. Due to automation controlled from a central motherboard, we have a chance for better electrical wiring that can improve energy distribution throughout the plane. And lastly, we will potentially have less manual components for controlling the aircraft, which will reduce the aircraft's weight and therefore the fuel required to burden the weight. Now over to Jaden to conclude.
Thank you, Stefan. So to conclude, I would like to remind everyone briefly about the 4 changes that were made to the Airbus A350 that allow it to become more fuel efficient than the next leading models. First, we visited the Netherlands to discuss the variable camber wings that can change their position in order to optimize flight for any conditions. Next, we hopped down to Egypt, where composites were born, and explained how they're used in modern times to make aircrafts lighter and consume less fuel. Afterwards, we flew back up to Germany, the home of the first law of thermodynamics, to showcase that better jet engines can use less fuel for the same job. And finally, we flew all the way down to Dubai to discuss avionics and how it is used to reduce fuel. Eco-friendly aircrafts are important because they shorten transportation time and protect the environment. They make flight a much more sustainable option. So I guess with that, the final question I have for you today is, where would you fly next?